Let's conclude this module discussing the tools in MATLAB for solving least squares problems. Let's recap what the least squares problem is. There's a matrix A, which is n by m, a vector B, which is n by 1, and the goal is over all choices of m by 1 vectors, minimize the mismatch between ax and b as measured in the norm. If several different vectors achieve the same minimum mismatch, then among them, choose the smallest x. For the algorithms I'm going to describe here, small can be characterized in two ways: the norm or the smallest number of non-zero entries. In a few modules, we'll look at another way to characterize small. Let's consider all the scenarios that can occur. 1. The equation ax equals b has at least one solution. Therefore, the minimum value of this norm mismatch is 0. It's possible that only one vector achieves this minimum. In other words, ax equals b has a unique solution. Or it's possible that many different x vectors solve ax equals b and hence achieve this minimum mismatch of 0. The other alternative is that the equation ax equals b has no solutions. In that case, this minimum mismatch is some positive number. It's possible only one x vector achieves that minimum, or possibly many different x vectors achieve that minimum. One approach to solve least squares is the command P inverse A times B. Let's discuss the properties of this solution technique for the four scenarios. Suppose the minimum possible mismatch is 0. In other words, ax equals b has at least one solution. In the case there's only one vector that achieves the minimum, P inverse A times B chooses that x. In the scenario that many different x vectors achieve the minimum, then P inverse A times B picks from among those the one with the smallest norm. For the situation where ax equals b has no solutions and the norm of the minimum mismatch is positive, it's possible only one vector achieves the minimum, and P inverse A times B gives that value. If there are many different x vectors achieving the minimum, then P inverse A times B chooses from among all those minimizers the x with the smallest norm. An alternative algorithm is A backslash B. In the context of least squares problems, this should only be used when A is not a square array. Let's go over the four scenarios. First, the situation where ax equals b has at least one solution. If only one x vector achieves this minimum, then A backslash B chooses this x. If many different x vectors achieve the minimum, then A backslash B chooses from among all these minimizers the x with the fewest number of non-zero entries in its components. When the equation ax equals b has no solutions and the minimum norm mismatch is positive, then if only one x vector achieves the minimum, A backslash B chooses this x, and if many different x vectors achieve the minimum, A backslash B chooses from among all these minimizers, again, the x with the fewest non-zero entries. So those are the two manners in which you will solve linear least squares problems. You'll get some good practice in the quizzes as well as in the homework. Good luck.